welcome to Gifted and Science and Technology Physics class. I'm NC Joshua. Now, today we'll be looking at thermal expansion in solids. What is thermal expansion? Thermal expansion is the ability for a material to expand or to increase in its dimension due to the application of heat. Heat makes the molecules to vibrate faster and hence they increase, they expand. Now, please take note of this, that the expansion is due to increase in the vibration of the molecules when heat is applied. Now, we have types of thermal expansion in solid. This expansion occurs in length. It occurs, that's when we say in length, it means in one dimension. It occurs in area, that's in two dimensions. It occurs in volume, that's in three dimensions. Take note again, linear expansivity or linear expansion is one that occurs in length, while area expansivity is also called superficial expansivity, occurs in area, so it occurs in two dimensions, while volume, which is also called cubic expansivity, occurs in three dimensions. Now let's look at the first one, which is linear expansivity. What's linear expansivity? We said is the increase in length per unit length per degree rise in temperature, increase in length. How will I write this? It means linear expansivity is equal to increase in length. Increase in length is called change in length. Increase in length over original length, then times change in temperature. Take note again, increase in length per unit length, that's per original length, per degree rise in temperature. So this is equal to, this is the simple way to write it, change in length over original length times change in temperature. Now please take note of this, that new length, this is new length minus original length, that is change in length. So I can tell you that this can be written as change in length, change in length over original length times temperature change times temperature change. Another way it can also be written is that change in length is also called extension. Is also called extension over original length times change in temperature. Take note of this. It's very important to know this. Now, there is something that you still need to know. Change in length per unit length. Change in length per unit length is called fractional increase in length. So it can also be linear expansivity is equal to fractional increase in length, fractional increase in length. Now remember, you now have times 1 over change in temperature. Everything here is fractional increase in length, then times 1 over change in temperature. Now all of these are possible ways that this formula can be expressed. Now another thing you can do here now is, if linear expansivity equals L1 minus L0, that's new length minus original length over original length open bracket theta 2 minus theta 1, that is change in temperature. Therefore, we'll be having cross multiply, we have L1 minus L0 is equal to L0 open bracket theta 2 minus theta 1. You have is equal to alpha L naught theta 2 minus theta 1. Now, what is L1 equal to? This goes here, you have L naught plus alpha L naught, change in bracket, open bracket, theta 2 minus theta 1. Now, this will now give you L1 is equal to, what is common here? L naught, open bracket, this place becomes 1, plus I have alpha, open bracket, theta 2 minus theta 1. So this is the formula to get new length. This is for new length. This is new length. This is new length. Now take note of this, that this is how I can calculate my new length if I'm calculating using linear expansivity formula to calculate for the new length. So this is what new length is equal to. Now, what is the SI unit for linear expansivity? What is the SI unit for linear expansivity? Linear expansivity equals change in length over original length times change in temperature, which is equal to meters over meters Kelvin. Take note of that. Meters is for length. Original length is meters. Temperature is in Kelvin. This cancels this. So the answer is 1 over Kelvin, which equals per Kelvin. Some textbook can have it as per degree Celsius if they are allowed. So the SI unit equals per Kelvin or per degree Celsius. Now, what about area expansivity? Area expansivity. Area expansivity. Area expansivity. What about area expansivity? We represent area expansivity with beta. What is area expansivity? I can use my knowledge from linear expansivity to define area expansivity. This is the increase in area. Instead of length, it will become area per unit area per degree rise in temperature. I reiterate again, area expansivity is equal to this is the increase in area per unit area per degree rise in temperature. So how will I express that? I will say beta is equal to increase in area is new area minus original area over per unit area, that is over original area per degree rise in temperature. That is area expansivity. Now, if you take note of this, what do? Cross multiply, what do you have? I have A1 minus A naught is equals beta A naught change in temperature. Now, if you want to get what is A1, A1 will not be equal to, take this way, it becomes A naught plus beta A naught change in temperature. A naught is common amongst here, then I have A1 is equal to A naught open bracket 1 plus beta change in temperature. Now you see that it's all looking like my L1, but the only thing that is changing is my L1 is being changed with A1, that's new area. My L naught is being changed with A naught, that is my original area, while my beta, my area expansivity, which is also called superficial expansivity, is being replaced, unlike what you have here, is now being replaced by beta. Now take note, the SI unit for area expansivity, SI unit for area expansivity is still per Kelvin or per degree Celsius. Why? This is change in area. This is change in area over original area times change in temperature. So area, we cancel that area. You are now left with 1 over change in temperature. That's why it will always be per Kelvin or per degree Celsius. What about our volume? Volume expansivity. Now remember, in solid, expansivity in solid. If you want to define volume expansivity in solid, what will you say? You say it is the increase in volume. Now you can use this definition again, which we use in length. It will be increase in volume per unit volume per degree rise in temperature. So it will be V is equal to V1 minus V naught over V naught change in temperature. I reiterate, it is change in volume per unit volume per degree rise in temperature. So without wasting time, what will be our V1? If you understand how it works, our V1 will now be equal to V naught open bracket 1 plus, we now have it as gamma change in temperature. That is how we'll have our V1. Look at it. It looks like this, but now we are not changing our A and we are not putting our V. So this is now the new volume. Remember, the SI unit here is equal to per Kelvin or per degree Celsius. Why? Because volume cancels out volume. I'm now left with 1 over temperature. That's per Kelvin or per degree Celsius. Now, there is something I want you to note here. What is that I want you to note is that note this, very important, note this, that density is equal to mass over volume. Density is equal to mass over volume. That is, that is, volume is inversely proportional to density. If you check it here, density and volume, they are inversely related. So if I want to express this in terms of density, it will not be in this manner. Instead of my V1 here, I will have density naught, that's original density, is equal to, instead of my V original there or my V naught, I will now have my new density. Then I will now have every other thing unchanged. Every other thing unchanged. Take note of this. This is the way density is expressed. This is the way volume is expressed. This is the way area, the new area, is expressed. And I've shown you how the new length is expressed. Now, what about this? After this, there is a relationship between linear expansivity, area expansivity, and volume expansivity. What is the relationship between these three? The relationship is that area expansivity equals 2 times the linear expansivity, while volume expansivity is equals 3 times the linear expansivity. So it means that if I have an expression like this, so if I have L1 is equal to L naught open bracket 1 plus linear expansivity change in temperature. Now this is my L1. Then remember, what is A1? A1 is equals A naught open bracket 1 plus. Now instead of having beta here, which is this ought to be the right way. Now I can rewrite this as A1 is equal to A naught open bracket 1 plus, in place of beta I will put 2 alpha. So it's 2 alpha change in temperature. Now I can still do that for volume. What will not be that for volume? V1 originally is equal to V naught open bracket 1 plus gamma, that's cubic expansivity change in temperature. But remember, I can still write it as V1 is equal to V naught open bracket 1 plus, in place of gamma I'll put 3 alpha, which is 3 alpha change in temperature. Thermal expansion in solid and liquid. Now, number one says interpret the statement. What's the statement? The linear expansivity the linear expansivity of a substance is 0.00005 per Kelvin. What does this mean? It means that for every 1 degree rise or 1 Kelvin rise in temperature, remember what I want to say. For every 1 Kelvin rise in temperature, this substance increase in length by 0.00005. I say it again. It means number one, for every for every 1 Kelvin rise in temperature, the length of the substance increases by 0.00005. That's what it means. For every one rising Kelvin, that substance will increase by this fraction. Take note of that. Let's look at question number two. Question number two says, the length of a copper rod was 10 meters at 30 degrees Celsius. What will be its new length when it is heated to 50 degrees Celsius? Take linear expansivity to be this. Now remember, in our class, we said new length because we are looking at what will be its new length. New length, we said, is equal to original length open bracket 1 plus alpha change in temperature. So this would not be L1 is equal to, what was our original length? It was 10. So it will be 10 open bracket 1 plus, what is linear expansivity? That's 0.000, that's 0.000017. Then times, what's our temperature change? Is changing from 50, from 30 to 50. So that will be 30 minus 50. Now take note, I'm not converting to Kelvin, I'm just solving directly. So my answer will be in per degree Celsius. There's no problem about that. Now, so let's continue. What will not be, now remember there's a bracket outside. So L1 will not be 10, open bracket 1 plus 0.123417 times 20. That becomes that. So what becomes this? If you are multiplying this by this, now you have this takes off this to give you this. So I have L1 equal to 10, open bracket 1 plus, this will now be 0.12317 times 2. Now 2 times this is 14, 4 carry 1. 2 times is 2 plus that one, that's 3. So I have 0, 0, 0, then point 0 plus 1, all in bracket. I have 10 equals L1. So what's L1 equal to? 10 open bracket. This plus this become 1.00034. So this times 10, what becomes my L1? L1 will now be 10.0034 meters. So that becomes my L1. So this is now the answer to my new length. So if you check what's the difference between your old length and your new length, will be 10.0034 minus 10. That's the answer. Now please take note, this is our theta 2, while this is our theta 1. So it is theta 2 minus theta 1. So it's rather 50 minus 30. Now let's look at question number 3. Question number 3 says, two metals P and Q are heated through the same temperature. Take note of this word, through the same temperature difference. So they have the same change in temperature. If the ratio of linear expansivity, so linear expansivity of P ratio linear expansivity of Q is equal to 2 ratio 3. That's what this statement means. If the ratio of the linear expansivity of P and Q is 2 ratio 3, and the ratio of length of their length and the ratio of their length. Which length? Their original length. The ratio of their length is 3 ratio 4. So LQ, sorry, LP ratio LQ is equal to 3 ratio 4. That's the ratio of their original length. The ratio of the increase in length. What is the ratio of the increase in length? I hope you know that increase in length is change in length. That's what we call increase in length. Increase in length is change in length, new length minus original length. So now what is the ratio of the change in length of P to the change in length of Q? That's what our question wants us to look for. So the question wants us to look for the increase in length. Take note, increase in length is also called change in length. It's also called extension. Take note of that, very important. Now, so what do they have in common? Remember, they have the same temperature in common. So I will say the change in theta for P is equal to the change in theta for Q. This is what I need to solve this question. I know every other parameters and I will look for this guy. Now, remember, recall, what are we recalling? That linear expansivity is equal to change in length over original length times change in temperature. So let's make our change in temperature the subject formula because that's what they have that looks alike. So I'll cross multiply here. I have alpha change amount original length change in temperature is equal to change in length. What is now change in temperature? Change in temperature is now equal to change in length over change in length over alpha times original length. Is what our change in temperature is now equal to. So if change in temperature P is equal to change in temperature Q. Therefore, I will now say change in length over alpha times original length of P. This is everything for P. Now remember, everything here is this. Change in temperature equal to this. So now if this equals this, according to what our question told us, so everything here for P will be equal to change in length over linear expansivity and original length of everything of Q. So this is what I need to put in all of these parameters to now know what is this and this. Remember, this is what I'm looking for. I have this already. So this is for P and this is for. So now I'll be having change in L of P over what is the linear expansivity of P? This is this ratio this, so this is for this as this is for this. So for P is 2. So I have over 2 times what is the original length of P? Original length of P is for this, that's 3 times 3 is equal to change in length of Q over what is the linear expansivity of Q is 3 times what is the length of Q is 4 times 4. Now to make this solving very simple, 3 can cancel at 3, 2 here 1, 2 here 2. Cross multiply, what do you have? I have 2 change in length. 2 change in length of P is equal to change in length of Q. Now, what is now change in length of P over change in length of Q? Now, this will not be, let this come under this. Remember, there's an invisible one here. So let these two go under this one. Remember, I'm trying to bring change in L of Q to come under change in L of P. Then this 2 that is here will go under this invisible one. So what do I have? I have change in L of P over change in L of Q will now be equal to my 1 over 2. So that means that change in L of P ratio, change in L of Q is equal to 1:2. That's the final answer for question number 3. Now let's look at question number 4. It says a square plate of side 10 centimeter, meaning they give us the length. We are solving question 4. They give us length is equals 10 centimeter. Now, if length is 10 centimeter, what is area? Area is length times length, which equals 100 centimeters square. That becomes our area. Now, it said the square is square diagonal plate of side. This is the length. Side 10 centimeter is made of a metal. The plate was heated from 30 degrees Celsius to 100 degrees Celsius. Full stop. The question is now the area of one face of the plate will increase to dash. So we are looking for what is now the increase in the plate after being heated. So now they gave us linear expansivity. They did not give us area expansivity. They give us linear expansivity. So you know that area expansivity is equal to 2 times linear expansivity. So now you know that beta is equal to change in area over original area times change in temperature. Beta, which is area expansivity, equals change in area over original area times change in temperature. What is beta? Beta, if beta equals 2 alpha, so I can now have it as 2 alpha equals change in area, which is now our, let me put it this way, as change in area, it will help us better, over original area times change in temperature. Now let's put this into consideration. It means 2 times, what is our linear expansivity? 2 times 10 raised to the power minus 5. 2 times 2 times 10 raised to the power minus 5, this is it, is equal to our change in area over, what's our original area? Our original area is this, 10 centimeters square. Now, if I want to retain my answer in centimeters square, I can continue and I will not change it to meter square. It's allowed. If my options are in centimeters square, I can leave it that way. But if I can solve to the end and convert it to meter square, so now it becomes over, what is the original area, which is now 100 times, what is the change in temperature? Is changing from 30 to 100. So it will be open bracket 100 minus 30. So this will now be equal to 2 times 2 is 4 times 10 raised to the power minus 5 is equal to change in area over, this will now be 70 times 100. That's now 7,000. 70 times 100 becomes 7,000. So cross multiply this, we'll now have 4 times 10 raised to the power minus 5 times 7,000 is equal to change in area. Now look at this. How do you solve this? This becomes 4 times 10 raised to the power minus 4 times 7 times 10 raised to the power 3 is equal to change in area. Now minus 4 plus 3 will be minus 1. So what is 4 times 7? 4 times 6 is 24. 4 times 7 is 28. So now it will be 28 times 10 raised to the power minus 1 is equal to change in area. So now our change in area is equal to 2.8 centimeters square. Now that means if I'm solving for change in area, which is equal to new area minus original area, and we have 2.8 centimeters square is equal to A1 minus 100 centimeters square. So what is my new area? My new area will now be equal to 100 centimeters square plus 2.8 centimeters square. So that will now become 102.8 centimeters square. So this is my new area, but this is the additional increase or the change in the